Good afternoon everyone. Myself Sirsat Sonali Sirsat in Physics Department for S.V.K.T College Devali Camp, Nashik. We have to studied in a previous lecture for the recap here. I can write expression for the electric intensity, expression for a electric intensity due to a volume charge distribution. This is the volume charge distribution, and the volume charge distribution here we have to study it for the electric intensity, for the volume charge distribution, surface charge distribution, and the line charge distribution. Is the equation for the electric intensity for the E vector into R vector is equals to 1 upon 4 pi epsilon naught. Integration for the volume charge distribution is the V for the R vector into dV dash upon a magnitude of the R vector into R vector is R magnitude of its cube. Magnitude of the R vector its cube into R vector is the volume charge distribution. Next, I can study it for this today's session for the Gauss's theorem. Second point, Gauss's theorem in electrostatics. We know the Gauss's theorem. Gauss's theorem for electrostatic for the depend on the surface charge and the charge element for the volume distribution, or charge distributed in the volume charge. Okay, volume charge density or volume charge distribution. This Gauss's theorem is in electrostatics state that the Gauss's theorem in electrostatics is state that electric flux for phi passing through a closed surface closed surface is equal to the Q upon epsilon naught. This is the Gauss's theorem in electrostatics for this statement, and this is the phi flux is equals to, for electrostatic, is equals to Q upon epsilon naught. This is the equation number 3. This is the Gauss's law in electrostatics equations. Then next is the Gauss's theorem in electrostatics for the two forms. First form is the integral form, and second is the differential form. First is the integral form. I can write here integral form. In integral form, the total electric flux in a small element, total electric flux or electric flux passing in a small element is the small element is the ds is the small element, then the electric flux is the d phi e is equals to electric intensity into small element is the s, and then the electric intensity or electrostatics in that the integral form for the integral form for the electrostatics for the Gauss's law for the integral form is the, or a small element passing through the electric flux passing through a closed surface is the d phi e is equals to E vector into ds is the surface element. Then the electric flux passing through a closed surface for the electric intensity is the closed surface is the integration of the E vector into ds vector, and here Q is the charge for the volume charge distribution or the surface charge distribution. Then the integral form of the Gauss's theorem is the integration of closed loop is the E vector into ds vector is equals to q upon epsilon naught. This is the integral form of the Gauss's theorem. Equation number 4. Equation number 4. Next is the, and then the electrostatics means the electric intensity for the closed surface or charge is electric flux passing through the small element is the E vector into ds vector is equals to q upon epsilon naught. Q is the charge and epsilon naught is the permittivity. And then the electric flux passing through the closed surface or outside from this the closed surface, then the electric field in the surface is equals to 0 for the outside closed surface, outside the closed surface, outside the closed surface, then the electric intensity E vector into ds vector is equals to 0 or electric flux also 0. Then integration of closed loop E vector into ds vector is equals to 0. Second form is the differential form. Second form is the differential form. Second is the differential form. In this form is the volume charge distribution is the small volume element V, and the charge is distribution for the charge is the Q is distributed from the volume V, and the volume charge density is equals to rho into V. Then the volume charge distribution for the Q is equals to integration of for the volume charge distribution rho into dV is the volume charge distribution for the charge is distributed for the volume. This equation number 4. This equation put in the above equation means the equation number 3rd. The equation number 3rd is the integration of closed loop into E vector into ds vector is equals to q upon epsilon naught. This is the equation number 3. Put equation 4 in equation 3rd. Therefore, the integration of closed loop for the integral form for the Gauss's law, then the integration of closed loop into E vector into ds vector is equals to 1 upon epsilon naught, and this values put this here. Then integration of closed surface V into rho into dV. Equation number 4th. Equation number 4. We know the Gauss's divergence theorems. Gauss's divergence theorem is the integration of the E vector into ds vector is equals to integration of the del vector into E vector. Equation number 5. This Gauss's divergence theorems put these values in this equation, means the equation number 5 put in equation number 4. Therefore integration of the del vector into E vector here into volume charge, here V, and this is the surface charge distribution, and here dV. This is the dV is equals to 1 upon epsilon naught. Integration of the volume charge is the rho into dV. Then this is the volume charge. Next is the differential form for the Gauss's law is the dV get cancel and integration also cancel. Therefore, the del vector or divergence of this Gauss's theorem is equals to del vector into E vector is equals to rho upon epsilon naught. Equation number 6. This is the Gauss's theorem for the differential form, and the next is the divergence of. This is equation for the divergence, and this also divergence theorem is equals to divergence of E vector is equals to rho upon epsilon naught. This is the equation number 7, and this equation for the differential form for the Gauss's theorem in electrostatics. For the Gauss's theorem is the true, but it is not used for use in always cases. And thank you.